MCT 4C, Vectors Day 7, we're going to do some forces questions. Very similar to what we did yesterday. And probably my strongest suggestion would be to solve these using components. The horizontal and vertical components can be quite a clear way of solving these problems. For the first example, we have three forces which are working here, A, B, and C. So if we were going to do the regular way, drawing the resultant, let's just do that here. If we were to draw the resultant for A and B, we would have to find it. And then we would match it with C, and we would come up with our answer here. And we'd have a lot of drawing and redrawing to do. It's fine, but you'd have to be very careful. So what we're suggesting that we do for this problem is to do the components of each one, the horizontal separately from the vertical, and then putting it together and coming up with the resultant. So let's look first. For A, they suggest that we look at the horizontal of each force. And then we'll look at the vertical for each force. So for A, it is 10 newtons, 30 degrees from the horizontal. So for our horizontal, we will write vector A, horizontal. And we want to know its magnitude. If you remember for horizontal components, because we are looking for this component for A, whoops, I drew a little too long, should stop right there. We know the 10, we know the 30 degrees, and we are looking right beside it. So we are looking at adjacent, we know hypotenuse. For a horizontal component, we use the cos ratio. So for vector A, it is 10 newtons. The angle between 10 and the horizontal is 30 degrees. That would tell us our horizontal component for vector A. Likewise, for vector B, the horizontal component would be vector B. We want this component right there. Again, I draw it too long. And we are using cos. So for vector B, we are doing 15 newtons, cos again, and this time 35 degrees to the horizontal. When we get our answers for both of these, our horizontal component will be to the right, or positive, to the right, for vector B as well. For vector C, the horizontal component is going to be to the left, and we should keep that in mind. Vector C has magnitude of 12, cos 42 degrees. Those three will give us our horizontal components. First one, 10 cos 30, is approximately 8.66. The horizontal component for vector B is approximately 12.3. And the horizontal component for vector C is approximately 8.9. It is to the left. So the horizontal component for our resultant would be 8.66 to the right, 12.3 to the right, and 8.9 to the left. So we have a total of, can't talk and type at the same time, 12.06 to the right. So I added the 2 to the right and subtracted the 1 from the left and got a total of 12.06 to the right. For my vertical, I think I'm going to just write it down here. Okay, let's do it on this page. My vertical for vector A for vector B and for vector C. I want to know this component right here, this component right here, and that component there. So I'm using the same angles and the same magnitude, I'm just using sine between them. So the vertical component of vector A is 10 sine 30. For B, 15 sine 35. And for C, 12 sine 42. For the vertical component for A, it is exactly 5. Oh, that's cool, but not what I wanted. There we are. For B, it is approximately 8.6. For C, it is approximately 8.02. The vertical component for A, and for A is an up, for B is a down, and C is a down. So when I want to find my vertical component for the resultant, I have to be careful with my ups and downs. I'll put my two downs together. So I have 16.62. Down and up I have 5. So I'm going to do my 16.62, take away 5, 11.62 downwards. Okay. So we want to put that information together. So for our resultant, I have 11.62 down. And I have 12.06 to the right. So my resultant, I'm going to take one so it's tip to tail and move it. The resultant is there. If I want the magnitude of my resultant, I have created a right angle triangle with verticals and horizontals. I can use Pythagorean theorem. So to find the magnitude of my resultant, I have 12.06 squared plus 11.62 squared, and I have my resultant as a magnitude of, is the square root of 280.5-ish. Magnitude is approximately 16.7. Down and to the right. We were asked in A to find the horizontal and vertical components, find the resultant of the horizontal components, and find the resultant of the vertical component. So we did all that by adding ups and downs, lefts and rights, putting that together in a diagram. And we are working on D, finding the magnitude and direction of the resultant. We have the magnitude. We just need to find the direction. So I would like to find theta in that corner. Again, we've got right angle trig. Whenever we're using components, we can use right trig, which is awesome. I can see opposite and adjacent. My tan ratio always seems to be working for me. Tan of theta is opposite over adjacent, which is 11.62 over 12.06. Second function tan of that ratio my theta is 43.9 degrees. It's not behaving today. So we can say that the resultant is 16.7 newtons, 43.9 degrees below the horizontal. Example number 2. Go. Let's get rid of it. All right. 2 wires support a stoplight. The tension forces in the wires are as shown. Find the resultant force holding the light. So we have force number 1. I'm going to call him little f. Is pulling upwards and to the right, both. I have a second force, which I'm going to call little g, who also pulls upward, but to the left, holding up that stoplight. We're going to determine the resultant force acting on the light by using components. So let's do horizontal. And vertical. So I want to determine the horizontal component of little vector f. I want the horizontal component of little vector g so that I can determine the resultant horizontal component. I want the vertical component for f, the vertical component for g, which will both be upwards, so we can add them, so that I can determine the resultant vertical component. For my horizontal, we use cos. We are determining the force going this way. So for F, it's going to be to the right. My force for F is 699. To find the horizontal component, we use cos because it's adjacent, and the angle is 79 degrees. For G, I am looking for this horizontal component. I am going to use 192. Again, I use cos for horizontal, 46 degrees. It will give me a horizontal component to the left. So when I have calculated those, I will subtract to get the resultant component. My horizontal component for F is 133.4 approximately. 192 times cos 46 is also 133.4. So that when we have the right subtract the left, neither is stronger. We have a 0 horizontal component. That makes sense. That light is not being pulled to the left or to the right. It has an equal force in either direction. For our vertical components, we have, again, we are looking for the upward force, the upward force given by G. Those will both be upwards, so we will add them. For little f, our vertical component is opposite in hypotenuse, so we are using 699 sine 79 degrees. For G, 192, sine 46 degrees. And my two answers for those, 699, 686.2, and 138.1. So the upwards force would be 686.2 plus 138.1, and we have a total upwards force of 824.3 newtons upwards. it would be safe to say, since that light is likely not headed upwards into the sky, that there is an equal and opposite force holding that light down, likely its weight with the force of gravity holding it down. Let's look at our third example. Example 3, not 13. Two ships collide on a foggy night. The SS Thorburn is sailing north 70 degrees east and hits with force of 50,000 newtons. The SS Caledonia is sailing south 40 degrees east and hits with a force of 78,000 newtons. Find the magnitude and direction of the resultant collision force. We are going to solve this in two different ways. First, again, we are going to use components. I would like to have a little diagram here to help me with this problem. We have the Thorburn, and it is sailing north 70 degrees east. So he heads due north, turns 70 degrees towards the east. Okay, that is our Thorburn, and T, and it is 50,000 newtons. Let's draw north, south, east, and west. Okay. If he turns 70 degrees towards the east, that means there's 30 degrees here. Okay, so I have an idea what the Thorburn is doing. The Caledonia is sailing south, turn 40 degrees towards the east. That one should be longer. Okay. 40 degrees east of south. And this one is 78,000 newtons, and that is the Caledonia. Okay. So that gave me an idea of what's going on. If I want to find my components so that I can use right-angled trig to solve this problem, I want to know the horizontal components and the vertical components so I can put them together. Horizontal for vector t is its magnitude, cos, the angle between it and the horizontal, which is 30 degrees. The magnitude of the other vector in a horizontal direction is its magnitude, cos, the angle between it and the horizontal, so I need to use 50 degrees. I need to use the angle here because I am looking for that horizontal component right there. Those two answers are, sure we're in degree mode, 50,000 cos 30. It's approximately 43,301.3 newtons towards the right. The other boat is 78,000 cos 50, which is approximately 50,137.4 newtons, again to the right. So my resultant, since both are to the right, would be adding those two together. Approximately 93,438.7 to the right. Vertical. We are looking for this force and that force, and we will be using the same two angles but sine for vertical. So the vertical component for the Thorburn is 50,000 sine 30. And for the Caledonia, will be 78,000 sine 50. $25,000. Approximately 59,751.5. For the Thornburn, it is an upwards, or more accurately, northern force, and for the Caledonia, it is a downwards or southern force. So the resultant we will get from subtracting. The downward force is larger, 59,751, take away 25,000, is 3,751, sorry, 0.5 down. So we have the components for our resultant. We can put them together and determine the resultant force. So I have a force to the right, 93,438.7 newtons. I have a downward force of significantly smaller than that, 34,751.5, down or south to be more accurate. The resultant is here. We would like to determine its magnitude and direction. We have created from vertical and horizontal a right angled triangle, so I can use Pythagorean theorem to calculate the magnitude. So I will square those numbers and take the square root. That's a really big number. Square root of the answer. Magnitude force is approximately 99,691.7 newtons. The direction is going to be south of east. We will call it theta. We can use right angle trig again. I'm going to use opposite and adjacent. So tan of theta is opposite, 34,751.5 over 93,438.7. Theta is approximately the inverse tan of that ratio. About 20 degrees. Therefore, the resultant collision force is 99,691.7 newtons on a bearing of 110 degrees. The second method for doing this is using the Coase law again, not components. So I would like to draw my diagram again and see which one of these two methods you like the best. So north. I have the Thornburn, and it is, let's go back a page because I'm forgetful. north 70 degrees east. And I made another error, hope you caught it. North 70 degrees east does not put a 30 degrees in here. Come on, you. It puts a 20 degrees in here. But since we did the whole last question and finished it, we want to compare our answers. We're going to go back and change the question, and you're not going to tell anybody. This is now north 60 degrees east. That will give me my nice 30 degrees. Telling me. All right. That is the Thornburn. The Caledonian was south 40 degrees east. So if we're going to add these two together, I want tip to tail, south 40 degrees east. Head directly south, turn 40 degrees, and there I have my result. This one should be a lot longer. It had a much greater force. I'm going to create one pretty one. Had a much greater force. Just adjust that a bit. There we go. 40 degrees just in here. The resultant. Okay, I have drawn my two vectors. I have lined them up tip to tail, and my resultant will be starting here, ending here from rules of vectors. I have to use the Coase law in order to be able to solve this. I know the two values. The Thornburn is 50,000. The other one is 78,000. I need to know this entire angle in order to use the Coase law. I have 40 degrees in that corner. I know that this Z pattern gives me 30 degrees here, and that mistaken 60 is right there. So in my triangle, I have 100 degrees. To determine the resultant, I'm going to use the Coase law. 78,000 squared plus 50,000 squared minus 2 times each one of those. Coase 100 degrees type it in. 28,000 squared plus 50,000 squared. I believe in my brackets. Really big number again. The magnitude of R is the square root of that number. 99691.8. Interesting. Same as before. We would like to be able to tell the collision direction. I would like that angle right there. Let's call it theta. I can't use right angle trig, but I can use the sine law. Okay, for direction. Sine of 100 degrees over the resultant is sine of theta over 78,000. Multiply both sides by 78,000. times sine of 100 divided by 99,691.8. We will get approximately 0.77052. Theta is the second function sine of that answer. Which is approximately 50 degrees. Since we knew the 30 degrees was above the horizontal, we must have another 20 degrees below the horizontal. So we know this 30. We know the total is 50, so this must be 20 degrees in here. That means we have a bearing of 110 degrees. We have an identical answer to the last time we did this problem. So whether you like components and do things separately, less difficult math but more writing, or you wish to do it this way using the cos law and the sine law, you just have to be very careful with your diagram. Please try page 58, number 2, 9, 10, and 15, and 5.10.1. That's online.